Let's learn how to make and read a phase graph. So we're going to start in quadrant 1 because when we're looking at adding heat, you either have heat or you don't, and you have time or you don't. You can't really have negative heat or negative time. And there are negative temperatures, but we'll look at those in a minute. So heat or time is on our x-axis, temperature is on our y, and we're going to have basically 3 lines: a diagonal, flat, diagonal, flat, diagonal. The bottom diagonal is solid, the middle diagonal is a liquid, and the final top diagonal is a gas. And what this shows us is as time goes on, we add heat and the temperature would increase, so we would get to the melting point and a solid would turn into a liquid. And as we would continue to add heat, we would get to the point that the liquid would vaporize, and then we would go to gas to infinity. If we were to remove heat, then that gas would condense into a liquid. The liquid, if heat was more removed, would freeze into a solid. And then the substance would stay a solid until negative 273 degrees Celsius, which is considered absolute zero. So this way that this graph looks at these lines and what they mean is going to be the same for all substances. The thing that's going to change is how we label the melting point and the boiling point. So we can see here at the melting point of 0 that is where solid will turn into a liquid and liquid will turn into a solid as we add heat or remove it over time. And the boiling point as well, liquid will turn to gas or gas will turn into liquid as we add or remove heat over time. And so liquids will never get colder than the melting point or hotter than the boiling point. They will just stay at that temperature until the phase change has completely finished itself all the way to a gas or cooled all the way to a solid. So here we have carbon dioxide. Again, thing looks exactly the same, except carbon dioxide's melting and boiling points are actually negative. So you can see here now we're back into quadrant 4, negative 56 for a boiling point and negative 78 for a melting point. So if we were to look on planet Earth, the hottest day on planet Earth is 70.7 degrees Celsius, and the coldest day on planet Earth is negative 89.2 degrees Celsius. So on the hottest day on Earth, 70.7 is well above the boiling point of that substance. And the coldest day is actually well below the melting point. And so on the coldest day on planet Earth, CO2 is actually solid. If you were to go to Antarctica, the carbon dioxide would fall out of the sky and snow down onto the ground as solid CO2. And then the hottest day on planet Earth, the carbon dioxide is actually in gaseous form. So part of the reason plants cannot live in Antarctica is because the carbon dioxide is actually a solid part of the year and they can't take that in. Liquid is always between melting and boiling point. So oxygen has even colder melting and boiling points. We have negative 218 for melting point and negative 189 for a boiling point. So because the coldest and hottest temperature here on our planet is actually above the melting and boiling points, oxygen is always in gaseous form on the planet Earth, which means no matter where we go on Earth, we are always able to breathe the oxygen here, which is good news. If it was colder than 189, there would be pools of oxygen laying around, and then colder than the melting point, we would have solid chunks of oxygen. Let's look at HDPE plastic. I believe this is number 2. If you see, the hottest day on Earth is still cooler than the melting and the boiling point, as is the coldest day on Earth. And so because of that, HDPE plastic is always solid on planet Earth naturally, unless we artificially heat it like my children did here when they melted some beads in the oven. Then we have the substance of sand, and sand will melt at 1600 and boil at 2230, which are both above the hottest and coldest days on Earth, and so we always see sand as a solid unless you again artificially heat it to a very high temperature, and then you can get sand to melt into glass, which is what they do when they blow glass, and then that liquid would be there. If you wanted to boil it and get clouds of sand, it would have to get really hot. Iron has really high melting and boiling points, higher than we see on planet Earth, and so we consider iron to be a solid, but if you heated it up enough, like in the center of the Earth, we get lava. So solid, liquid to gas, right? As we add heat, the solid will reach that melting point, which is the temperature that it turns to a liquid. If you add heat to a liquid, it will reach the boiling point, which is the temperature that it will turn to a gas. So liquids only exist between the melting and the boiling point for any given substance. Gases are things that are above the boiling point, and solids are when the substance is below its melting point. So if we remove heat from a substance, right, then if we get to a melting point, a boiling point, it will turn into a liquid. If we get to a melting point, it will turn into a solid, right? So the phase changes happen at those two temperatures for a given substance. Finally, the last thing that I kind of like to think about is with substances like oxygen. I like to think of oxygen, because its boiling point is so low, it's like oxygen already boiled, which is why we always see it in gaseous form on Earth. So things like helium, hydrogen have such low boiling points, we just think of them as gases, but we could certainly cool them down into solids or liquids if we got cold enough. We just don't see that temperature on the planet Earth. And tungsten has a really high melting point. So we think of it as a solid, but if you got it above 3422, you would be able to melt it or even eventually turn it into clouds of tungsten.